Okay, so about signals. About signals, let me open the slideshow here. What? Why is that one there? Okay, good. About the slides overall, basically, I use the Creative Commons licensing here, so it means that, well, you are free to use them, you can free to share them. Don't change your name in my place. Just share it as is. We are fine. If you are starting to use these for commercial purposes, my lawyer will be contacting your lawyer. Okay, so now you have me warned. So basically, but please feel free to use them. And actually, I think I have also given permission to comment if you find any problems you didn't understand. Please comment these slides that I can actually fix them, make them more usable. Okay. So, that's annoying text down there. So, digital signal properties. That's a kind of, hey, we are in Japan. You understand this perfectly with manga. This is not my manga. Manga. Okay, so there's a cat or it's not cat, it's a katakon or something like that. With the superpowers of singing something, and there's a spying dog thingy bone, and that's basically a digital voice recorder here. How to do a voice recording? What kind of parts you need there? You probably have already gone through some fundamental electronics, right? So if you have a microphone, it gives you very tiny signal in millivolt level, I'd say 100 millivolts or so, and which means that basically what you need to have is some sort of amplifier first for the signal. Next step would be to have a low pass filter to get rid of some noise. Then you need sample and hold, and then A to D conversion. Usually, when you're looking at a A to D converter chip, it usually have at least these parts on it already. If it's a to D converter designed for voice, then it has all of these parts. And usually nowadays, that's adjustable by some software interface. Same for that one. The sample and hold automatically works with this A to D conversion thing, and of course, somewhere there's a sample and clock. Okay, what the signal looks like. So before going into that amplifier, it's a small one. If you will take a look at on a oscilloscope, it looks tiny and probably a little bit noisy. On the next step, it's just bigger, nothing more than bigger. After low pass filter, and you get rid of some of that spurious peaks, which are at high frequency. After sample and hold, it basically it just samples the current value and keeps the value for the A to D converter under that. And then basically on the last step, it's the analog to digital converter makes the digitation. So it basically quantizes these levels in the closest possible bit. Okay, that's the process for voice recording. On the first page, for first stage, basically, we are still talking about analog signal with continuous time and continuous value. This one here is sampled signal, meaning it's discrete time. So sampling time or sampling frequency defines the places where the signal is defined. But it still has the continuous value, and that's basically how it relates to this original signal x of t. So we have the basically sample time ts times an index. This index is directly the table index. When you put those in the memory, you have the index 0, 1, 2, 3, 4, 5. And that actually basically is tabulated data in computer memory. And the last one here is the digital signal, which is in addition to discrete time, it's also quantized value. Okay, so it's not the real value what the signal had, but the closest what you can represent with that A to D converter. Most of this course, actually all the 5 exercises we have is more about discrete time, but almost continuous value, since we are using floating point accuracy. Going to this one would be a little bit more advanced topic, but if you are interested in, say, this quantized signal and what they will do, you should then take that extra part, which is called embedded DSP. Okay. And there's a cat. Yeah, sampled signal. Sampling rate, that defines the sampled signal, and the sampling interval is simply TS is 1 over sampling rate. Okay. Then there's the so-called Shannon's theorem. This is actually from the data transmission theorem. Shannon was a data transmission guru, which basically states that you must take at least 2 samples per original signal period in order to show it correctly. And there's the effect of aliasing in case you don't. So the blue one would be the analog signal. And sampled, if you take the samples on 2 small number of spaces here, you will actually get only this kind of envelope, and as you can see, it's not the same signal anymore. So you must actually make sure that you are sampling fast enough for the signal. If not, you need to basically take those high frequency components before sampling, or or something like this will happen. And by the way, this sampling, this is basically also true for digital signals. If you are resampling a signal, so for example, you have first the 44.1 kilos samples per second sampling rate audio signal. Then it's digital, right? Then you want to basically resample with lower sampling rate to reduce the amount of memory needed for storing the stuff. For example, you cut it to half. Sampling rate goes down by half. If you do not take care of this high frequency components from the original signal, you will get aliasing effect on that digital pre-sampled signal. Okay. Yeah, digital signal. digital signal, actually there's only one really interesting thing, how the signal to quantization noise ratio is defined. That gives basically the noise floor for your signal. So signal to quantization noise ratio is simply this one. So it's 1.761 plus 6 times n, where the n is the number of bits, meaning if you have 8-bit A to D converter, 8 times 6 is 48. Is it 48? Yes, it's 48. So you basically, you get about 50 decibels of signal to quantization noise ratio. Okay, 50 decibels. If you think of your hearing, that 50 decibels is enough actually for spoken voice, since this spoken voice is quite monotonic. 8-bit bits is enough. But how about a symphony orchestra? What is that? The very low volume parts and very high volume parts. The dynamic range can be 100 decibels. You cannot store 8-bit resolution, the symphony orchestra, or any music actually. Or maybe some bad music, it might sound a little bit better if you store it with 8-bit, since you lose something. It must be better, or not that bad at least. Okay, but anyways, signal to quantization noise ratio. This actually gives you some sort of hints of the how many bits you need to have in order to have a high quality signal. Okay, example. Shannon's theorem actually gives you the lowest sampling rate that you should use in order to have a good quality CD quality signal. Okay, that's where the 44.1 kilohertz sampling rate comes from. It comes directly from the fact that, okay, people can usually hear between 20 and 20 kilohertz signals. So you need at least 40 kilohertz sampling rate. Why it's 44.1? There are historical reasons why it's exactly like that. But actually, it also means that when you have 44.1 kilohertz sampling rate, there's some error margin that you can actually put the this low pass filter before sampling. So you have 20 kilohertz, the low pass filter cutoff frequency, and you can have it steep enough so that you reduce the amount of these higher spectral components so that they wouldn't alias into the signal. Okay, so that's why CD quality basic sampling rate is 44.1. Then there are these higher frequencies, the sampling rates. So higher is usually better in here. Okay, and then about the CD quality again. Oh, okay, CDs actually. Well, how many of you have any CDs anymore? I still have, but I bought them on last century. Yeah, that's the last century technology. But anyways, it's still referred as CD quality. Okay, even of these, on your players, MPEG players and stuff. Yeah, mini disc. Yeah, that was 115 kilo samples. But okay, less bits. It's a little bit different, since it compresses the data by taking the differential first. But anyways, yeah, then you need higher sampling rate actually. But anyways, yeah, so listening music. Sound pressure level normally between 20 and 100 dB. that depends, of course. The symphony orchestra have, almost whispering level sounds, which is, well, 0 dB is whispering. Actually, pin drop to floor or 1 meter and listening it from 1 meter away, it's about 0 dB level. And then, okay, 80 dB absolute level would be the one that you shouldn't go higher in continuous time. More than 100 dB will destroy your hearing for good. Okay, but anyways, so CD quality PCM signal has 16-bit resolution. 16 times 6 is 96, right, plus 1 processor. So it's almost 100 dB signal to quantization noise ratio. Okay. So that's where those numbers come from. Okay. Some words about basic signals. So fundamental signals that are used to represent or test a system. In analog world, in electronics lab, you might have actually, or well, you haven't seen that, nobody has. It's the original Dirac delta, very mathematical tool to actually do some magic things for the data. And well, Hero could give you a 2-hour lecture on Dirac's delta and its applications. Okay, it's continuous time, but anyways, it's present only on occasion 0, and whether it goes to infinity, but in a way that the energy is actually 1. When you integrate it over time, or of the space from minus infinity to infinity, it actually gives you the mass is 1 or energy is 1. Okay, in discrete time systems, this is actually something really tangible, since basically it's still the same, it's sampled form, but it's sampled by integrating those, not just taking a sample, but integrating this. And the discrete Dirac's delta function, or discrete delta, it's simple. It's actually the same meaning. It's an impulse function, meaning it has a value 1 on when the index goes to 0. Otherwise, it's 0. This is actually the most usable test vector of all. The digital systems are basically defined by the impulse response. That's one way of actually defining them. And that's the most important way of defining. Since basically if a system is linear, I'll go with the linearity later, then you can find out what the system does by just taking the impulse response, meaning you feed in impulse and see what comes out. You know exactly what is inside of the system. On analog electronics lab, you probably have done something with the Laplace transformations and square waves. And that was ugly to try to find out how this system, analog system, actually relates to this some of those Laplace transformation. That's nasty exercise. I hope you don't have to do it anymore. But on digital world, this is easy. Another important signal is actually unit step, because, well, it's just sample form of the unit step function or Heaviside function in analog world. And this one now resembles a square wave. To test systems on laboratory, well, that's probably what you usually do. Device under test, you take the function generator and see with the oscilloscope what the output looks like. for the waveform you get out. Right. So basically, the this unit step function is just sampled Heaviside function. Useful test vector for testing the systems. Did I have the no, I did not. Okay. So basically, there are also a couple of the dependencies here. So to get discrete delta function, you can actually have the unit step function and then just subtract this part out. So you have a unit step, then you would have the time delayed unit step, meaning one step that way, and if you do the just a differential of those, you will get delta function. Which means on this page, if you have a sampling oscilloscope, so this is actually digital sampling oscilloscope. What you can do, if this is actually the Dirac's delta, oh not Dirac's, but the not delta function, the Heaviside function, or close to that one, the step function. Step function actually is right that edge here. This is then the what you have the digital sampling oscilloscope shows that the response for Heaviside. If this is linear system, then you can simply take whatever you got out here. So it's f of t, which is actually now the f of n, since this is the sampled signal. If you take the difference f of n and just a differential of it, meaning the just the time delayed f of n, what you get is the impulse response, meaning that, well, if you have the signal source, square wave signal source, digital sampling oscilloscope, have the data available to some program, you can actually find out exactly what this system does. It defines the whole system. Okay. And then there's some mathematics also about any arbitrary signal, but anyways, let's go forward. Okay, next thing. So we have these special signals, the impulse or step functions are available. But how about the periodic signals, so sinusoids, or this would be, well, sinusoid plus the third harmonic, I think. Okay, some harmonic distortion there. So basically, that's how the periodic signal is defined. So if you can find a constant value that you get x of t same as the time shifted x of t always, then you have a basically periodic signal, and the shortest of those will be called base period. Same thing in sampled. Sampled signals, that time space is discrete, meaning the indexes, which means that the periodic signal would have an index n, which is a constant value and integer value to do that same thing, which basically means this practically means that on digital domain there are no periodic signals. They are never exactly mathematically sense periodic, unless they are coming from the same source as your sampling clock. Okay, just keeping that in mind. So they basically, although the signal is periodic in analog domain, it's basically never periodic in digital domain. That's the practical stuff. But well, it looks kind of periodic with some say artifacts. Okay. Wow. Who cares about those Fourier series? Why on earth I have that one? Okay. So yes, basically, okay. So Fourier series, of course. If you have periodic signal, you can represent it like that one. But yes, as I said, there is no such thing as a periodic signal in discrete time space. Okay, so the rest of the signals, so we have these basically periodic signals, sampled periodic signals, which are not necessarily periodic anymore. Then we have the delta, and we have the heavy side, or the unit step signal, and the rest of the signals are actually called random, more or less. So random means a real life signal that you do not know what the next value is. So it's unpredictable values, and you can only measure the statistical and spectral properties of such signals. And this is actually our signals, what we are going to analyze and process. Some examples where those random signals are coming from, actually one is if you are, well, audio, wind noise in microphone, meaning small Q turbulence on mechanical structure will cause some noise. There are some noise reduction technologies. If someone tells you about noise cancellation technology, that ain't existing. You can reduce, you can never remove noise. You can reduce it only. And that's actually a couple of other facts. This you can do measurements, but on those you already know that you cannot do exactly noiseless system. Shot noise in electronics. Shot noise comes from the current carriers. Electrons. Yes.
Can you cancel the noise by turning the phase of the audio by?
No. Well, you can cancel the noise by, turning off the equipment. Yeah, but that's reduction. It's not cancellation. They are calling the cancellation, but it's reduction. Cancelling for me means that it's, you don't have any of that anymore. But evidently it works. The air, especially on aircraft, also noise cancelling things, but you still can hear some of that. It actually does pretty good job. Yeah, 20 or 20, 30, 40 dB. Business class 40. I know it. I got a free upgrade. Last time I got the free upgrade on the airplane was 20 years ago. So, wow. Okay, I'm still excited. Shot noise in electronics, it comes from the current carriers, meaning the electrons. Those are, quantized size carriers, which means that you always have some noise. If you have some current on circuitry, you also have noise. And yes, you have current on your circuitry. Okay, another source, noise source in any electronics, Johnson noise, meaning if you have a resistor in your circuit, yes you do, otherwise it would be kind of funny circuit. And if it's above the absolute zero temperature, you will have noise. Okay, so you will always have some noise on the system. Okay, random signals. So the nature of random signals, actually, say natural processes. Well, digital processes usually are, well, yeah, this is kind of digital, or quantized processes are basically following the Poisson distribution, meaning that, you know, uh, it's how many times it appears, for example, that kind of events, or rolling a dice or something like that. Flipping a coin would be, well, binomial, but follows the Poisson distribution. But then basically, if you have bigger numbers of any any random numbers, it will eventually, follow more or less the normally distributed random numbers, which means that, well, this is actually also gives us nice way to simulate noise. So we can add some noise to a arbitrarily made signal, so we can do some noise reduction. That would be actually fun to try the noise cancellation there. Okay. Yeah. Statistical analysis, a couple of reminders. The histogram of a statistical or a random value or any value actually would give you the how many, well, what is the frequency of each value on this of the data, meaning the basically how many values on that random data are actually zeros, how many ones, how many values are twos, and so on. That's the Poisson distribution. The same thing for this the normally distributed random numbers, but now we have basically we can use any values. We just have a region of, for example, from between 2 and 2.1, you have that many times of the value appeared there. Okay, so that's basically how this Gaussian shaped Bailey curve comes to the represents the how the values are distributed on that normally distributed random numbers. Okay. Okay. Couple of other things. Now, we are still talking about the signals. One important measure of or the best kind of measure of a similarity between signals is correlation. So basically, if you have two signals, X and Y, if you calculate the correlation, you can find out how well those signals are correlating, meaning how similar are they. Application on that one. For example, trying to find a leak in a pipe, gas pipeline or such, you can use acoustic correlation technique. So basically, if you have a pipeline and somewhere you have a leak, it is a noise source, random noise source. And then setting a couple of microphones, one in here, another maybe there, or basically they can be on the others at the same side. You basically have the sound waves from the same source coming to these 2 points at a different time. Okay, then basically what you need to do is calculate the cross correlation. And at some the time difference, you basically have a correlation peak, meaning that you have the same these signals with the time difference. You will have the basically matching the phase at some point. Otherwise, it's random, meaning it does not correlate. So basically, measuring that peak, you will find out the distance difference. Basically, that is the halfway. You can find out that distance. And now you don't have to dig out the whole 100 meters of that pipeline. You just need to dig it in one spot. The spot that is wet. Okay, that system is actually used in real life, especially on the factories. Okay, or oil refineries actually. That's where I know this is used. Yeah, cross correlation. Another important correlation is the autocorrelation, meaning the self-similarity. Does a signal have a similarity with itself? Application. How about a system that has a loudspeaker and microphone, right, just like that. And then you have the some surface here. Now you get the reflection back. So basically, you have direct the signal from the loudspeaker next to the microphone, and then you also have this reflection. So it means that you will again get a kind of correlation peak somewhere here. Well, you get huge peak here, but don't worry about that one. This is directly proportional to the distance. All right, isn't that nice to have that kind of equipment in your car when you park them? So that's the same as the distance sensor, ultrasonic distance sensor in your car. It's based on that kind of technology. Well, it's more like a flight time, but anyways, the same effect. Good. So correlation. And then again, say, although nowadays this say Fourier technique of calculating correlation is almost obsolete because of the high power computing is even in the wristwatch. But anyways, if you have a lot of data sets, then basically using Fourier transformation would be giving the faster result. But okay, I don't know if you need to worry about that. Yeah, acoustic radar was one example. Then another important, say, process or function on the signals would be convolution. Convolution is defined as, well, you reverse the time on one signal and then multiply it with the other one, calculate sum. So it's quite close to the correlation, except that the time is reversed on the other one. Okay, what is so important on that one? Well, if you take a look at the Fourier space, meaning if you want to have a signal filtered spectrally, you actually want to multiply the signal spectrum with a desired filter spectrum. That's actually what it means, this mathematical mumbo jumbo here. But anyways, that translates back to linear convolution in time space, meaning that now we have a method to calculate these filter output in time space. You do not have to go into frequency space doing these ugly calculations. You do everything in time space using convolution. Not too many slides, don't worry. About the signals again, one important measure of quality of signal is signal to noise ratio. And that's the definition. It's basically power of signal divided by power of noise, and log of 10 of that one, and 10 times. Yeah, you're familiar with that, right? And if the signal and noise variances are known, then basically you have the signal variance squared is directly proportional to power. Okay, so the variance squared, oh, no, variance is, sorry. So this is variance, not variance squared. Variance is directly proportional to the signal power. Okay, so remember that one. When you calculate variance, you're actually measuring the power of the signal or noise. We'll practice a little bit of that one on the exercise. Lots of stuff here. What is spectrum analysis then? Well, spectrum analysis basically is a method to calculate how much you have, what is the power distribution of signal cut in the frequency space. And it's simply just a Fourier transformation. Okay. And then we go back to this fact that periodic signal is not periodic when you digitize it. This was exactly 1000 samples per second. The sampling rate, 50 Hertz signal. It gives the peak here. Okay, but it does not look exactly periodic since it has these funny envelopes because of the digital signals are never exactly periodic. One is the sampling rate does not match this frequency exactly, and another one is when you do a digital sample. Digital sample and calculate something, it's always limited time, only within some limited time, meaning that you are always multiplying your signal with a box, and that gives you some effect on the frequency response or spectrum. Aha. More tools. Doesn't it look nice? Spectrogram. If you take a spectrum, it looks like one single line here, color-coded. So 0 frequency up to the highest frequency you can sample, so sample rate over 2, and color-coded values. If you have a signal which has a varying frequency like a chirp, then basically you would like to see how that frequency is varying on the signal. So this basically gives you the idea of how the frequency is changing by time. If you make just a simple spectrum of the whole signal, it will be flat. But adding the time information into it, breaking into smaller sections and calculating the frequency response, the spectrum for each of those small sections will give you more informative picture. By the way, this is the foundation for voice recognition. You basically take subsamples of a voice sample and then start correlating the images. Each of the vocals and vowels actually have a different shape picture on the spectrogram, and then you start correlating those with say pre-recorded samples of spectrograms. Then you can actually start finding the correlation. Okay. Haha. So that was the theory part of the first sessions, and next we will take a lunch break. So if you have any questions, now is a good time to ask. So it was for lunch, right? Okay, thanks. So we'll be back at 1:20. Let's change that a little bit. So 1:20 p.m. we'll be back, and then basically I will go through the first lab exercise tutorial. Okay.